This is Precalculus section 3.6 notes. Today we're going to be talking about rational functions, and these are functions that we've actually talked about many times throughout this year, and I promised you previously that we would get more information later about vertical asymptotes and horizontal asymptotes and when and where they appear in functions, and we finally arrived at the section where we're going to do so. So we're going to start with the parent graph of our reciprocal function, f of x equals 1 over x. Okay, we know what that looks like. It has, it has a point here at 1, 1, and a point at -1, -1. It has a point at 1/2, 2, and a point at 2, 1/2. So one branch looks like this. And then the other branch has a point at -1/2, -2, and -2, -1/2. And that branch looks like this. Okay? And then we also know that we have an asymptote, a horizontal asymptote here at 0, and a vertical asymptote here at 0. So our vertical asymptote is the line x equals 0, and our horizontal asymptote is the line y equals 0. And again, more about those asymptotes in just a few minutes. But first, let's talk about the end behavior of this function. Okay, so we could, kind of go around in a circle here. I'm going to start here, kind of at this point down at the bottom. I'm going to call this spot number 1 to coincide with that spot number 1 here. So my y values here are shooting down, so going to -infinity, as my x values are getting closer and closer and closer to 0. And I'm going to put this little negative sign there. What that means is that the graph is approaching 0 from the negative side of 0 or from the left. Okay, then as we continue around clockwise, my y values are approaching 0 as my x values are approaching -infinity. And then up here at the top, this is going to be position number 3. Again, my y values are going to be shooting upward, so that's approaching +infinity. As my x values are approaching 0, we're going to put a little plus after it, right? Because the graph is on the right side of 0, so we are approaching 0 from the right. And then finally, position number 4 over here, my y values are approaching 0 as my x values are approaching +infinity. So now let's talk a little bit about asymptotes. So first of all, vertical asymptotes occur at values that make the denominator undefined, right? So anything that would make my denominator equal to 0 is going to create a vertical asymptote in the graph. So if you don't have anything in the denominator, you don't have a vertical asymptote. But if you have any variable in the denominator, you're going to have a vertical asymptote somewhere. So in our parent graph, f of x is 1 over x, the denominator is x, the value that makes the denominator 0 would be if x were 0, therefore we have a vertical asymptote at that value. Horizontal asymptotes have a few more rules. These are determined by the degree of the numerator, which we will call n, and the degree of the denominator, which we will call d. So first of all, if the degree of our numerator, n, is less than the degree of our denominator, for example, let's say our function was f of x is 2 over x, so we have a constant term over an x. The degree of the numerator is 1 less than the denominator. Or here's another example. F of x equals x over x squared minus 1. So both of those have a numerator degree smaller than a denominator degree. In those situations, the horizontal asymptote will exist at y equals 0. So in the case of our parent graph, f of x is 1 over x. The degree of our numerator was less than that of our denominator. Therefore, our horizontal asymptote was at 0. what if the degree of our numerator is greater than the degree of our denominator? For example, what if we had f of x equals x squared minus 4 over 2x? So the degree upstairs is 2, the degree downstairs is 1. We are going to have no horizontal asymptote in this situation. And then finally, the third situation, I'm sure you are wondering, well, what if the degree of the numerator is equal to the degree of the denominator? For example, what if we had f of x equals 3x squared minus 2x minus 1 over 2x squared plus 3x minus 2. Degree of the numerator is 2, degree of the denominator is 2. Then our asymptote here is going to be y equals 3 over 2. Look carefully at my function. My lead term of my numerator was 3x squared. My lead term of my denominator was 2x squared. The ratio of the leading coefficients was 3 over 2. And that is where my horizontal asymptote would be if the numerator and the denominator have the same degree. So let's put this information to use here in a problem. The example says to find the x and y intercepts of the rational function. So our function g of x is going to be 2x minus 5 over x plus 7. Remember, if we're finding an x-intercept, we are putting in 0 for y. So this is going to look like 0 equals 2x minus 5 over x plus 7. Okay, but I want you to remember that a fraction equals 0 when its numerator equals 0. The denominator can equal 0 or it would be undefined. So really, we can just ignore that x plus 7 and we're looking at where does 2x minus 5 equal 0? If you were to solve that equation, you would add 5 and you would divide by 2, and so you would get x equals 5 halves. So that's my x-intercept. 5 halves or 2.5. For my y-intercept, I am going to put 0 in for x. So this is going to give me y equals 2 times 0 minus 5 over 0 plus 7. Well, when I simplify that, 2 times 0 is 0. 0 minus 5 is negative 5. And on the bottom, 0 plus 7 is 7. So my y-intercept is going to be the point negative 5 sevenths. Or if you were graphing and you needed to know where to put that on your coordinate plane, you just type that in your calculator. That's going to be negative 0.71. Okay, so just a little review on x and y intercepts. Okay, another example. We have f of x equals x squared minus 25 over x minus 2. Sorry about that. So in this example, the degree of our numerator is 2, the degree of our denominator is 1. Okay, if we're going to find an x-intercept, again, we're going to set y, or f of x, equal to 0. So we're going to write, we're going to write 0 equals x squared minus 25 over x minus 2. But again, remember, a fraction equals 0 when its numerator equals 0. So we really only care about the x squared minus 25 part. So we're going to say, when does x squared minus 25 equal 0? Well, if you added 25 to both sides, and then you square rooted both sides, you would get x equals plus or minus 5. So we have two x-intercepts. We have one at positive 5 and we have one at negative 5. Our y-intercept is when x is 0. So this is going to be 0 squared minus 25 upstairs and 0 minus 2 downstairs, which again is going to simplify to negative 25 over negative 2, which would become positive 12.5. All right, so now let's talk about asymptotes. We just reviewed x-intercepts and y-intercepts. Let's talk about asymptotes. So in this equation, in the numerator, we have 2x minus 3. In the denominator, we have x squared plus 3x plus 2. The first thing I notice is that my denominator can be factored. So I'm going to go ahead and factor two numbers that multiply to make 2 and add to make 3 are going to give me x plus 2 and x plus 1 as my two factors. So because I have two values that could make my denominator 0, this tells me that I'm going to have two vertical asymptotes, because again, vertical asymptotes are going to be values that make the denominator equal 0. So I'm going to have a vertical asymptote at x equals -1 and at x equals -2. Okay, now for the horizontal asymptote, remember that the degree of my numerator is 1 and the degree of my denominator is 2. So the numerator is less than the denominator, which tells us that we are going to have a horizontal asymptote at y equals 0. So if we were graphing this, the first thing I would do is I would sketch in my asymptotes, and then I'd look for x-intercepts and y-intercepts, and then I'd start making a table to plot points. So that's exactly what we're going to do in the next example. Here we have a new rational equation. First, vertical asymptote at the value that makes my denominator equal 0. So I know that that's going to be at x equals -2. Horizontal asymptote, the degree of my numerator and the degree of my denominator are the same, n equals d. So remember that this is going to be a ratio of the leading coefficients. Well, the leading coefficient of the numerator is 1, leading coefficient of the denominator is 1, so I'm going to have a horizontal asymptote at 1 over 1, which is just 1, right? My x-intercept, I set the fraction equal to 0, so 0 is equal to x minus 3 over x plus 2. But again, I'm really only concerned where the x plus 3, or excuse me, the x minus 3 is equal to 0. So if 0 is equal to x minus 3, then x is going to be equal to 3. And finally, my y-intercept, when I plug zeros in for the x's, I end up with -3 over 2 or -1.5. Okay, so now I can go ahead and I can start plotting all my information. I'm going to begin with my asymptotes. I have a vertical asymptote at x equals -2. That's right here. Highlighters are great for asymptotes. I have a horizontal asymptote at y equals 1, which is right there. Okay. I have an x-intercept at 3, so 1, 2, 3. And I have a y-intercept at -1.5, which is right there. Okay, so now what it looks like is I need some more points because I need to know what's going on. Most likely, since I have this crisscross of asymptotes, I'm probably going to have a branch in the upper left quadrant and the lower right quadrant. But in order to know for sure, I just need to start plugging in some points. So I'm just going to choose some x values, -5, -4, -3, -2, -1. I already know when x is 0, because when x is 0, that's going to be my intercept. So that's already -1.5. I know that one already, so I don't need to put that in my table. So then I'll go 1, 2. I also know x is 3 because that's an intercept, so I'll skip that one. And I'll do 4 and 5. Okay, and I already took the time to plug these into the function and simplify them on my calculator. So I'm just going to go ahead and I'm going to give you what these values are. And this is 2 2/3, 3 1/2, 6, undefined, right? Because that's where we have our vertical asymptote. -4